Okay, so today we're going to be talking about the Hooke's Law post lab. This is the lab that we did in class involving the springs, and where we check to see the relationship between the spring force and how far a string is stretched. So I started the unit talking about energy, and we defined it as a conserved substance-like quantity with the ability to cause change. And this is the conceptual definition. Now, like most of the things we talk about in class, a lot of the terms that we have also have a graphical definition, and this is the case too. So here we have that energy is also the area beneath a force versus displacement graph. So that's a graphical definition of energy. And in this video, what we're going to be talking about are the different ways that energy can be stored based on different forces. Okay, so the first graph we're going to look at is the spring force versus the stretch graph. And what we found from the lab is that we've got a linear relationship between these two things, the positive slope, and we defined in class the spring constant, K, as the slope of this graph. And what K means is the stretchiness or the stiffness of a spring. So a high spring constant is going to be an extremely stiff spring that's hard to stretch, and a low K, a small K, is going to be a spring that's very easy to stretch. Essentially, if you have a very high K value, a very high spring constant, if you stretch it 1 meter, you're going to get a larger force than if you had a small K, then you stretched 1 meter. That would give you a smaller force. So for each graph, what we're going to do is we're going to look at a force and a displacement graph, since we're defining our energy as an area beneath the force versus displacement graph. So this time we're going to be talking about the spring force. Every time we take a look at this, what we're going to do is note a change observed. So in this case, change that we're going to see is a spring being stretched or compressed. So in this case, energy is being stored in the spring, and there's going to be more to this later in a different video where we talk about problem solving with energy. So if we're going to be talking about the area of this graph, what we have here is essentially a triangle. If I could shade this in. And we're interested in this area. So what we would find is that the area of this triangle is 1/2 base times height, right? That's the area of a triangle. So what we'll see here is that this triangle has a base of change in x, and it has a height of fs. Okay, so from our spring constant equation, we know that this fs is also equal to k delta x. So what I'm going to do is substitute that in so that we have 1/2 change in x, or the stretch, times k times change in x. And what I'm going to do is I'm going to group these together, group the x's together, and I have 1/2 k times this stretch squared. And this is what I'm going to call E sub s. And this is the energy stored elastically in a spring. Okay, the next change that we're going to be talking about is the change that we see when you raise an object and you change its height. So what we're concerned about is the change in height of an object. In this case, when we observe this type of change, we're storing energy in the Earth's gravitational field. Okay, and from this point forward, you'll often see me just abbreviate it as storing energy in the Earth we're actually storing it in the gravitational field, but the Earth for short. So to get this equation, we're just going to get the area of this graph. So if I shade this in, this will make a rectangle. So our area for this graph is just base times height. And what we see is that there's a base of change in y, and it's just called y because we're talking about a vertical change of position. So that's why it's a change in y, and then we've got times the height of FG. Substituting in a few things, I have to change in y times our FG, which is 9.8 newtons per kilogram times mass. And then what we'll see, I'm just going to rearrange a few things here, is mass times 9.8 newtons per kilogram times change in y. And if you're in honors, you'll see I'll usually just write it like this. In regular, I like to just use a h for the change in y, but essentially they both mean the same thing. We're just talking about a height here. Okay, so these two equations mean exactly the same thing. So depending on the class I have you for, you'll see me write it both ways. And this is the energy that's we're storing gravitationally. The next change that we're going to be talking about here for this slide is when an object is accelerated from rest due to constant net force. So when we do this one, there's going to be a few more steps than the previous ones. The change that we're going to see is the object's motion. So we're putting energy into an object by accelerating it from rest. So when we talk about where this energy is stored, we're saying that it's stored in the moving object. Now, the shape for this one is also a rectangle. And the force that we're talking about when we're accelerating something is going to be the net force here. So here, we've still got the area of base times height. And this area is equal to the base of the change in x times the net force, which we know the net force is mass times acceleration. So I have mass times acceleration times a change in x, moving things around. Now, one thing you'll notice is that we have an equation where we see a and change in x together. So I'm just going to write that off to the side here, where we see that we've seen this equation in our v squared is equal to 2a delta x plus v initial squared equation. Now for this derivation, what we're going to do is we're saying that the object is accelerated from rest. So this term goes away. And what we're left here is v squared is equal to 2a delta x. Getting a delta x by itself, we have that a delta x is equal to 1/2 v squared. Now what I'm going to do is I'm going to substitute this into here, and I have mass times 1/2 v squared. So I'm going to clean this up by just pulling the 1/2 forward. This one gets a subscript k. And this is the final form of this equation. This is the energy stored kinetically in a moving object. So our equation for this one is EK is equal to 1/2 mv squared. All right, so we've got one more to do today, and this one is the change that we're observing is anytime we see heat or sound created due to friction or collision. So in this one, we're going to be talking mostly about friction, and the place where this energy is stored is in both the object and the surface. So again, we have a rectangle like usual, like the last few. Area again is base times height. This time our base is changed in x, and this one's a much shorter derivation. All I'm going to do is bring the force of kinetic friction to the front times delta x, and this is it for that one. And this is the energy stored internally. So the INT here, subscript INT here, means the energy is stored internally in the object and in the surface. So these two things are always in your system whenever friction happens. Now we're talking about both because when two objects or two surfaces are rubbed together, you could try with your hands. When you rub them together, you'll feel heat in both your left and right hand. So technically, it's most correct to say that when an object is sliding on the ground and experiences friction, it creates heat in both the surface of the object and the floor it's sliding on. Okay, so moving forward and collecting everything that we just talked about, here we've got our energy storage modes in our leftmost column. These are the terms that we're going to be responsible for knowing how to use, and the different ways that energy can be stored. So we have energy stored elastically in a spring, kinetically in a moving object, gravitationally in an object that has some type of height, and energy stored internally due to friction. Now you'll notice in this table, and you could pause this and study from it, there's a change observed, and there's a column for this for each energy storage mode. There's a change observed, and likewise, there's also a place where energy is stored, and there's an equation. Now, in the next video, what we're going to be talking about is our diagram that we're going to use to solve energy problems, and how you fill this diagram out and how you complete it is going to be solely based on your understanding of this table. So we'll talk more about that in the next video. So I'll see you later.